In this video, we'll have a look at the pricing of bond options, particularly of the log-normal type formulas that are obtained in Gaussian short rate models. Recall that an interest rate cap can be regarded as a portfolio of put options on zero coupon bonds. In fact, we showed that a caplet for the period from capital T to capital T plus delta T with a cap rate of R can be regarded as 1 plus R delta T many puts on the T plus delta T bond, where the puts have a strike of 1 over 1 plus R delta T and an exercise date T. Similarly, a swaption can be regarded as a put option on a fixed coupon bond. In particular, we saw that a swaption with exercise date capital T and a strike rate R can be regarded as a put option with maturity capital T and a strike rate of 1 on a coupon bond with coupon rate R, which pays coupons on the same dates as the underlying swap. Thus, in order to be able to price, and in particular, therefore in order to be able to calibrate to caps and swaptions, it's necessary to price bond options, both zero coupon and fixed coupon. Let's briefly review the log-normal option pricing formula that we will need below. Suppose that x is a log-normally distributed random variable, i.e. that the ln of x is normally distributed with mean mu and variance s squared. Earlier we showed that in that case we have the following expressions for the probability that x is greater or equal to k, and the expectation of the maximum of x minus k and 0, where d plus and minus take the following familiar forms. Now, by change of numerator invariance, the value of a call C with strike K and expiry capital T on an underlying asset S is given by the following. And as the denominator here is equal to 1, we can rephrase this as follows, where S hat here is simply the value of the asset S divided by the numeraire, which is the capital T bond, i.e. S hat is defined as follows, and Qt is the equivalent martingale measure for the T-bond. Now suppose that S hat has real-world dynamics given as follows for some deterministic volatility matrix. Recall that under the measure Qt, the process S hat is a martingale and therefore will have zero drift. As its volatility will remain unchanged, the dynamics of S hat must therefore be given as follows, where WQT is a Qt Brownian motion. Now this is a stochastic differential equation that is very familiar and can be solved using a Dolians exponential, and moreover, since the volatility matrix is deterministic, we'll obtain that S hat t is log normal under Qt, and that the ln of S hat t has the following distribution. I repeat again that the log normality here follows from the fact that the volatility matrix is assumed to be deterministic. Now, by the martingale property, it also follows that the Qt expectation of S hat at time capital T is just S hat at time 0, and therefore we obtain the following expression for the value of the call, where d plus and minus take the following form. Now we can replace S hat by its definition. S hat is S over the T bond, and thus we obtain the following result. If S hat, defined to be S divided by the capital T bond, is an Ito process with the following dynamics, and if sigma is deterministic, then the value of the call C with strike K maturity capital T on underlying security S is given as follows. We also obtain a formula for puts given by put-call parity. Consider now an affine short rate model of the following form, where the volatility of the short rate, sigma, is deterministic. This is a Gaussian short rate model, and examples of this are the Vasicek, the Merton and the Holy model, as well as the Hull-White extended Vasicek, but not, for example, Coxing or Solros. We would like now to price a call option C with strike K and maturity capital T on an underlying asset, which is the S bond, where the maturity of the S bond is greater or equal to the maturity of the option. Now in affine form, bond prices are given as follows, where capital A and capital B are deterministic functions, and it is an easy exercise to show that, applying Ito's formula, the bond price dynamics are given as follows, where we do not care about the drift because this will disappear using martingale properties, where this B is the B that appears in the affine bond pricing formula. In particular, it follows that the volatility of the bond, in other words minus B times sigma, is deterministic. Of course, a similar expression holds for the capital T bond. If we now deflate the S bond using the T bond as numeraire, then the volatility of P hat will be the differences of the volatility of the S bond and the T bond. In other words, it will have a deterministic volatility given as follows. We can now apply the formula on the previous slide to price the call option on the S bond with maturity capital T. Now for the Ho-Lee model, we found the following expression for capital B, and hence P hat has a constant volatility, which implies that the average volatility times the maturity is given as follows. For the Vasicek and the Hull-White extended Vasicek model, we found the following expression for capital B. And you can show from there that the deflated S bond has a deterministic volatility given as follows, and therefore an average volatility times maturity given by the following integral, which can be evaluated exactly. We now have seen how to price zero coupon bond options in the Merton and Vasicek model, as well as the Ho-Lee and Hull-White extended Vasicek models, and therefore we are now able to price caps and floors in those models. Next we consider coupon bond options. We have already mentioned that a caplet is equivalent to a put option on a zero coupon bond, and that a payer swaption is equivalent to a put option on a coupon bearing bond. Jamshidion's trick is a method which transforms an option on a coupon bond into a portfolio of options on zero coupon bonds. But note that it is restricted to one factor models, where the T-bond price is a strictly decreasing function of the short rate. This is the case, for example, in affine term structure models. Here is the result. Suppose that Ck tau is the time t value of a call on a coupon bond B, where tau is the expiry of the call and k is the strike. Notice that we use curly letters for the coupon bond, the call on the coupon bond, and the strike. Suppose that the coupon bond pays an amount yi at date ti, where tau is less than t1, which is less than t2, up to tn, i.e. yi is either a coupon on a coupon date or the coupon plus the principal at the terminal date. In that case, we can use numerical methods to compute that value of R star, which has the property that the value of the bond at the expiry of the option, given that the short rate value is equal to R star, is exactly equal to K. In other words, that value of R star for which the call option on the bond expires exactly at the money. Using that value of R star, we then define the strikes Ki as follows. i.e. Ki is the value of the Ti bond at time tau, given that the short rate is R star. In that case, we will show that the value of the call on the coupon bond is equal to a sum of call options on the Ti bonds. Here CKTS, using straight letters rather than curly letters, is the time t value of a call with strike K and expiry capital T on a zero coupon bond. So these are calls on zero coupon bonds where the strike is Ki and the maturity is tau, and the underlying asset is the TI bond. Before we proceed, notice that the coupon bond price at time tau is given as follows. Here yi are the cash flows after time tau. And since each of these zero coupon bond prices is strictly decreasing in the short rate R, so is the coupon bond price. It therefore follows that one can find a unique value of R star for which it is the case that the value of the coupon bond at time tau is equal to the strike of the coupon bond option. In that case, R star, for example, can be found via a root finding algorithm, e.g. the bisection method or Newton's method. Now let's tackle the proof. Observe that the payoff of the call at its expiry is given as follows, where the price of the coupon bond is given by this sum. Now let R star be the unique value of R tau for which the call expires at the money, i.e. let R star be that value of the short rate which solves this equation. And then define Ki as follows. Observe that the sum of the products of yi with ki is just equal to the sum of yi times a zero coupon bond, and that is the value of the coupon bond at time tau, given that the short rate is R star, which by definition of R star is equal to k. We now consider two cases. The first case, the short rate R tau that we observe at time tau is strictly less than the critical value R star. In that case, because bond prices are decreasing functions of the short rate, we have that the value of the coupon bond at time tau that we actually observe is strictly greater than the value of the coupon bond using the short rate R star, which is k. In other words, the option on the coupon bond will therefore expire in the money. By exactly the same reasoning, we have that the zero coupon bond price at time tau, using the actual short rate that we observe, R tau, will be strictly greater than the zero coupon bond price using the critical short rate value, which is by definition is Ki. And therefore, each of the call options on zero coupon bonds, these here, will expire in the money. In other words, if the call on the coupon bond expires in the money, so does each of the calls on the zero coupon bonds, and hence we see that the payoff of the coupon bond option, which expires in the money, so we don't need this plus, can be rewritten as follows, using the fact that the sum of yi times ki is just equal to this curly k, and that's equal to the payoff of the options on the zero coupon bonds. The second case is if the short rate that we observe at time tau is greater or equal to the critical value. In that case, the coupon bond price is less than k, i.e. the coupon bond option expires out of the money. Similarly, the value of each of the zero coupon bond prices that we observe is less than or equal to ki, and so each of the zero coupon bond options expires out of the money as well. And thus we obtain that the coupon bond option has a value of 0, as does each of the options on the zero coupon bonds. So what we see now is that in both cases the payoff of the coupon bond option is equal to this linear combination of payoffs of zero coupon bond options. And thus in either case, at the expiry date tau of the coupon bond option, we see that the value of the coupon bond option is equal to the value of a portfolio of options on zero coupon bonds. Now, by the law of one price, if two portfolios have the same value in the future, in all states of the world, they must have the same value now. And thus, by the law of one price, the value of a coupon bond option is equal to the value of a portfolio of options on zero coupon bonds at all times before the expiry of the option. And thus, if we are able to price options on zero coupon bonds in a one-factor model where bond prices are strictly decreasing functions of the short rate, we will also be able to price coupon bond options and therefore swaptions.